Hello, AP Stats. We are working on Chapter 5, Section 5.2, Anticipating Patterns, Probability. And we're going to go through real quick a couple definitions here and then get on to some problems. So here we have probability describes the chance that a certain outcome of random phenomenon will occur. And so keep in mind, probability is also known as long-term relative frequency. Random phenomena are those where their outcomes are unpredictable in the short term, but a pattern emerges in the long term. So we've talked about random a little bit. Know that it is not the same thing as haphazard. The word random, we use it all sorts of ways nowadays, but it's a description of the type of order that only emerges after a long time has passed in the long run. So that's what we're talking about in probability. How many successes have you had out of all possible outcomes in the long run is what your probability is. Do know, as I'm sure you know already, probability should always be between 0 and 1 inclusive. So you shouldn't end up with a probability over 1. And so, of course, to find probability, we're going to denote it like this. Probability of A is the number of successful outcomes over the total number of possible equally likely outcomes. So a really simple problem to start. A small high school has 16 freshmen, 15 sophomores, 12 juniors, and 17 seniors. If a student from the school is selected at random, what is the probability that the student is a junior? So all we're going to do is add up here. We have 16 plus 15 plus 12 plus 17, 60 possible, and 12 of them are juniors. So of course the probability of being a junior is 12 over 60 or 0.2, and you can write it in either a fraction or a decimal, it doesn't matter. So easy, moving on. Also today in class we talked about simulation, and no, there's really a couple kinds of probability. Empirical probability, think of the E for experimental. Squeeze it in. Or if you're actually observed probability would be what you would find out from a simulation over time. What is the probability of something happening? Whereas theoretical probability would be more what you would actually be able to surmise before doing the experiment, or maybe it would be what you found after you did the experiment several times. So theoretical probability is often very easy if we have equally likely events. For instance, rolling a die. We know rolling a die that if it is a fair die, that 1/6 of the time we should get any given number. But let's take this example for instance. A thumbtack was tossed on the floor. What is the probability that it's landing with its point up? And so, of course, this isn't something that we could easily get a theoretical probability. We know there are two outcomes, point up and point down, but they might not be equally likely. So we could use empirical probability. We could toss that thumbtack over and over and over and over again and see what we get over time. Now remember, there's going to be, if you look, here's our results, we're going to have a lot of variability at the beginning. But as you get to, this has gone to like 10,000 tosses of that thumbtack, it's going to settle down really closely to what the theoretical probability. In this graph, that theoretical probability was 0.42. So about 42% of the time in the long run, the thumbtack would be landing point up. This is a good illustration of the law of large numbers. Very important theory in probability. Law of large numbers, make sure you write it down. says that as we observe more and more repetitions of a chance phenomenon, the proportion of times a specific outcome occurs approaches a single value, and value is the theoretical probability. So as you can see, as the number of times increase, we are approaching what our true theoretical probability is. Okay, here we're talking about complements. The complement of an event is the probability of the event not happening. So if probability of A is the probability of something happening, the probability of it not happening would be 1 minus the probability of A, which makes perfect sense. Know that the complement will be often abbreviated or denoted with a little c like this, the probability of the complement of A. So here with our thumbtack example, a thumbtack is tossed on the floor. What's the probability of it not landing with its point up? So we are looking for the probability of not point up, the probability of the complement of point up, if A was point up, would be 1 minus the probability of A, which is 1 minus 0.42 or 0.58. Easy, just subtract to use a complement, but make sure you know what a complement is. If A is the probability of it raining, the complement, of course, would be what's the probability that it does not rain. Okay, here before we look at this problem, I want to discuss a little bit what mutually exclusive or disjoint means. Notice these words, mutually exclusive, also known as disjoint, mean the same thing. And that's when you have two events, two things occurring, two events that can't possibly occur at the same time. For instance, you cannot be a freshman and a sophomore. Those are mutually exclusive. Those are disjoint events. You cannot live in Georgia at the same time you're living in California. Those are mutually exclusive events. So they're two things that cannot happen at the same time. So, and that brings us into talking about things that are happening, that are occurring, and how we would find those joint probabilities and putting them together. And sometimes you want to find the probability of this and this happening, and sometimes you want to have the probability of this or this happening, and those are the two major probability rules that we're going to use. So the first one's the addition rule. We know already that this symbol is a union, and it stands for the word or, so the addition rule is to find the probability of A or B happening. So know if you're finding an or, you're going to use the addition rule. You're going to add, this formula, by the way, is on your formula sheet, but you should easily know it. We're going to be using it so many times. The probability of A plus the probability of B, subtracting the probability of A and B. Remember, the upside down U shape is intersection, which means the word and. So think about that formula for a little bit before you move on. It makes sense if you want the probability of A or B happening, well, you would add the two probabilities together, but you'd have to subtract out the things that occur in both of them simultaneously, because you don't want to count that twice. That's that intersection you're subtracting out. Sometimes that's easier to see on a Venn diagram. We'll do that in a minute. So here we're given this table. These are so much easier to do with a table. You will not always be given a table, but I wanted to start a little easier. Table below shows the breakdown of students in a small school by class and gender. What is the probability that the randomly selected student will be a sophomore or a junior? So when you see that, you know you're going to use the addition formula. Probability of being a sophomore or a junior would equal the probability of being a sophomore plus the probability of being a junior minus their intersection, sophomore and a junior. Now we know already you cannot be a sophomore and a junior. And so if we look back up here, it talks about if two things are disjoint, the probability of A and B is going to be 0. So we just end up with, we need to find the probability of being a sophomore and add it to the probability of being a junior. We don't care about their intersection if they're mutually exclusive disjoint events. So what's the probability of being a sophomore? Well, here's the total number of sophomores, 15, over the grand total of people is 60. And here we have the total number of juniors is 12, over the grand total is 60. And so that is, of course, 27 over 60, and we could simplify that if we wanted to. Notice we could have found that without our formulas. We know here, right here, are the people that are sophomore or junior, and we could just put it over 60, and that's fine. You don't have to use a formula every time, but you need to be able to use it with and without a formula, because depending on what you're going to be given, sometimes you'll need the formula. But if you can look at the chart and do it without, that's definitely fine. Okay, and then next one here, what's the probability that a randomly selected student will be a sophomore or a girl? Probability of sophomore or a girl would be probability of being a sophomore plus the probability of being a girl minus their intersection, sophomore and a girl. Okay, now this time that intersection is important because you do have people in this group that are sophomores and girls. So we need to make sure we include, these are not just disjoint events. So if we look at our chart, the probability of being a sophomore we already found is 15 over 60. The probability of being a girl, well, we look along our chart, our girls, total number of girls is 32. Over the grand total of 60, minus what they have in common. See, right now we're counting this 8 twice. We're counting it as part of the total number of sophomores and the total number of girls. So that's why we have to subtract out one case, 8 minus 60. Sophomore and girls are these 8 people right here. So we subtract that and we get 39 over 60, which of course you could simplify. Oops, 60 to 13 over 20, but either way. Now notice you can definitely figure that out on the chart without using the formula. Pause the video a second and think about how you'd find that without the formula. Okay, I'd like to look at that same example. You do not have this on your notes, but just at the bottom of page 16, I'd like you to draw that same example out of the probability of sophomore or girl in a Venn diagram. So we're going to find 2 circles. We've got the sophomores, we've got the girls. These 2 circles are overlapping because they are not disjoint. They have something in common. If you do a Venn diagram of 2 things that are disjoint, you're going to have 2 circles that are not touching. Okay, so the total number of sophomores we had were 15, so everything in this circle has to add up to 15. So I'm going to start out with what they had in common. There are 8 sophomore girls, so there must be 7 out here, sophomores who are not girls. And then if we look at the blue girl circle here, there are 8 that they have in common. There were a total of 32 girls. So if we subtract out the 8, 24 of those girls are not sophomores. So again, we could find some probabilities here by just looking at this chart. When you are asked to do a Venn diagram, always make sure you put a box around it and have the grand total included. In other words, there are 60 total people in this sample in this school, and so we need to make sure all these numbers add up to 60. Since we had the sophomores and the girls all in the 2 circles above, we did not include circles for freshmen, juniors, boys, and so forth. We need to make sure that the remaining 21 people out of the 60, 21 plus 7 plus 8 plus 24 all adds up to 60. So who are these people here? These 21 people That would be the people who are not sophomores or girls, or neither, not sophomores or girls, would be 21 over 60. And that makes a lot of sense when we look at the 39 over 60 we got previously. That should add up to 100% of the people. Okay, stop the video here.